Assalamualaikum warahmatullahi wabarakatuh to all of my students. For today's lesson, we will see or we will discuss the tutorial 7 that I was give to you before. So for tutorial 7, we look at the relevant question related to our chapter, which is a principle of chemical equilibrium that we had previously learned in our previous chapter, previous class. So today we will discuss tutorial about it, where I already prepared 15 questions for all of you, and it is the variation. Question is in variation of easy to a difficult question. So it's mixture of it, but mostly most of the question is the application of the principle of chemical equilibrium towards our daily chemistry problem. So I hope that you already discuss or do the question entry before, so you will be more understand about these topics. So we will move to our first question. Where in this question, the question asks us to write the reaction quotient for the acidification reaction of following reaction. So the keyword is here. The keyword is reaction quotient. So for the reaction, so for this one, for the reaction quotient, so if we look back at in our general equation, we will have this one. So what is ln Q? Ln Q is a reaction quotient. It is basically ln Q is concentration of product over reactant, where if we look more detail, all the product matter must be either in gas or liquid phase. We didn't consider any solid species in our system. So if we have one, so we just denote it as a one. So what we need to do is we need to look at our chemical equation, and we need to balance. So here this chemical equation is already balanced. So what should we do is the Q is product over reactant, and then this is our product, and this one is our product. We have two product here, and this one is our reactant. So CH3COOC2H5 is the version of it. So we put like this, H2O over our reactant. Now the reactant is H2COH, so C2H2O5. So we put our reactant. So as we don't have any polarity, any mole here, so everything is one on one. So that's why we don't put anything here. So that's how we write a reaction quotient for according to the equation. And we move to the next question. This question asks us about the standard. So this question asks us about to calculate the standard reaction gives the energy of the oxidation of ammonia So we know to calculate the reaction given energy, what we need to do is delta G is equal to delta G product minus delta G reactant. And remember that we have number here, so it means that 4 mole of ammonia react with 5 mole of oxygen gas, and it will produce and gain equilibrium, 4 mole of nitrogen oxide and also 6 mole of water. So here is we have G product, delta G product minus delta G reactant. So our product now is nitrogen oxide and also 6 mole of water. That's why we do it like this, delta G and O plus delta G H2O minus summation of the reactant. So the reactant is ammonia and also oxygen gas here. So now what we did is we remember that we have this one of the coefficient for each species, so that's why we put it for delta G and O. So you don't need to put delta here for C and O. So here, you know that now we have 4 mole of nitrogen oxide plus 6 mole of water, and then minus in bracket, and this one is the summation of reactant, 4 mole of ammonia plus 5 mole of oxygen. Now what we need to do, we need to find each value of all of the species. So you can refer to the appendix, and I will leave it to you to answer this question. So you just plug in the number here, the number of reactant energy of nitrogen dioxide, water, ammonia, and oxygen, and you will get the answer for this question. And we move to question 3. So the question 3 asks us to estimate the fraction F of F6P fructose 6-phosphate in a solution where F fraction is defined as fructose 6-phosphate over F6P fructose 6-phosphate plus G6-phosphate, glucose 6-phosphate. So in the solution, so you can imagine that in a solution we have a mixture when we have G6P, and this G6P we turn to F6P. That's why in the solution we will have the mixture of G6P and F6P. So the question asks us to estimate the fraction of F6P in the solution, and the question gives the reaction equilibrium. It gives the equation of the reaction where the reaction in equilibrium at 25 degrees centigrade, given that delta GR not equal to 1.7 kJ per mole at the temperature. So to calculate this thing, as we know in this chapter, by have K, by doing all this value, we can predict the fraction or the composition of the species, of each species in this solution. So we need to remember this one. So by using all of the summation, we can compute, or we can calculate, or we can predict all the composition of the species in our solution. So now our species we have F6P and also G6P. So first thing first, what we need to do is we need to find the K, or the equilibrium constant. So for the K, we have a formula which is exponential is a function of negative delta G naught over RT. So here what we do is we just plug in all the number here. So now the formula, the question is in kilojoule per mole. So what we do is we need, where in this, so you need to be very careful with the unit. Now the unit here is kilojoule per mole. So what I need to do is I convert it to joule per mole. So that's why K equal to 10 power of 3. That's why I put in 1.7 times 10 power of 3 joule per mole. And our R gas constant is 8.3145 joule per kV per mole. And remember that we need to change this one to Kelvin unit. So what you need to do is you use 73 plus 25, so we can change it to Kelvin unit. So that's why we get 298 here. So our K constant is equal to 0.50. And by definition, we need to remember that K equal to product, concentration of product over concentration of reactant. So here we know that the G6P is F6P. So that's why I can write it K equal to concentration of F6P, where this one is a product of G6P, is our reactant. Then, so by definition, we know that K is F6P, concentration of F6P over G6P. And then what we do next is we divide the numerator and denominator by G6P over G6P, because if you still remember, because this one is equal to 1, so we can divide it. So here we can, once we divide it, we get it like this. F6P equal to F6P over G6P over F6P over G6P plus G6P over G6P. And G6P over G6P equal to 1. And F6P over G6P over G6P over, so here we will get this one, this number. So here the difference is this one. We need to be smart and how to use this relationship. And later on, we know by definition K equal to F6P over G6P. So that's why this one we can replace it with K. This one we replace it with K plus 1. So here we already obtained the K value. K is 0.50 over 0.50 plus 1. That's why we get 0.33. That's why we know that we can predict the composition of F6P in this species is 0.33%. And if you are repeated this one by using same equation, same method, you will get the G6P equal to 66 or 0.66. 0.66. However, we already know that the composition of F6P and G6P equal to 1. So we already get the F6P is 0.33. So by manipulating this equation, we already can determine the composition of G6P or the fraction value of G6P, where it's going to be 0.66. So if we convert it into the percentage, so we will get 30% for F6P and 60% for G6P respectively.